With that, I'm going to turn it over to John. I'll just say that this is John Olgin, and he is here to talk about his work, and it is super cool. John has been, doctor.
Oh, yeah, that's right. Yes.
Doctor, because it's a recently earned title, right?
Yes, this May.
Yes. So congratulations to
Thanks.
Dr. John Olgin. Am I saying that right? I think.
Olgin, yeah.
Yeah, okay. And so he's going to talk about it's part of your research, right? It was part of
Right.
your Yeah. So we're here for it.
Awesome. Great. All right. And I know actually two of my dissertation committee members are actually here online, so that's great too. So let me go ahead and just get started with what I got and kind of let me show you what's going on with this. So what I'm going to do is I'm going to do this presentation mode. Can everybody see the screen pretty well?
Yes.
All right, excellent. So basically what it is I'm going to go over some of the work that I did for my dissertation, and kind of give some ideas and some insight of what I learned from looking at the data, specifically cloud data that was actually collected back in 2020, and what kind of ways we could actually improve data quality when it comes to actually identifying clouds, and maybe that could be extended toward other parts of data collection in Globe. So, but I mostly focus with the Globe Observer app, and so this is basically my dissertation. So there might be a little bit data heavy, but I'll kind of go over some of the basics of what came out of the research that I had. So giving you just a quick outline of what I have, it's just an introduction. Of course, we all know about citizen science, so I'm not really going to go into too much detail with that, but just go straight into what NASA and what the Globe program does so far, and the success that it's had, and some of the things that were kind of interesting for me to take a look at and investigate a little bit more, as far as like getting more detailed analysis of what kind of data quality issues might arise when coming in and working with the Globe Observer data, and how we can actually improve that. And even some toward the end of the presentation, some really great ideas of doing that in a more constructive way, utilizing some other workshop ideas and techniques as well. So taking a look at what we're going to talk about is the objectives that I'm going to be covering over today. Objective one, basically going over some of the findings that I ran into looking at specifically looking at the Globe Observer cloud data collection. What were three top errors that I was able to encounter, and what kind of, well, not errors, but I guess you'd say like problems or people that were having some difficulty with identifying, and then finding objectives 2 and 3, finding ways to actually kind of figure a way to overcome those and see how we can actually better address those issues, how we can actually help those people who are Globe participants and getting involved more and learning more, and also collecting data better as well. And then objective 4 is taking all the results from the I guess you could say the intervention of actually introducing these new training techniques that to help with better data collection, how we can actually even improve on that, and then take a look at a further study regarding the new objective that I'm adding here at the bottom of this, which is looking at incorporating a little bit of a twist of what's called the model-based reasoning technique, which I'm covering just a little bit later on. So, like I said, NASA is a definite leader in citizen science. It's one of the things that drew me to the program initially, and really has actually here in the El Paso area, when I brought it into the physics and astronomy program, it grew, and I think there's a lot of people now looking at how can we actually get involved with it, especially this class that I just had with the eclipse data. They were so like really in tune with actually collecting data and learning more about science. And in fact, one of the meteorological students that I had in my class really took to it as well and started really playing with it more. And I think if we just keep this as a side note, NASA Globe program is a great way to actually address and bring it into the classroom and getting students really involved using basically the environment as a laboratory. And so that's basically what drew me coming back to the main topic here. A lot of the data that is collected through Globe is very useful. I mean, from the Zika program with the mosquito habitat, you're looking at basically how that data has actually helped with mitigating a lot of the spread of Zika and some of the other mosquito-borne diseases, especially down here in the El Paso area. We actually have West Nile virus that actually hit us. This is a great way to actually utilize Globe to help health experts in the field, and especially in this area, to really help mitigate these problems. Looking at the eclipse data just recently back in October, and the one that we're going to be seeing in April, great opportunity to see those effects and the weather effects of and environmental effects. Seeing the little critters coming out when the sun starts to dim, and then they realize, oh, we got tricked, and we're going to go right back underground. So, but there's a lot of things that we can actually use the data for and analyze, and that's one of the things that we've covered in the AGU talk. But I kind of wanted to talk a little bit more about the data quality issue that it's kind of arisen a little bit. And I know that there has been some things during this dissertation research that I was working at. I was looking at some of the overall like citizen science kind of issues that have been occurred in different various citizen science projects, and the three major ones out of the literature review that I was able to get from was basically looking at certain things. For example, if we kind of focus on clouds, some people are having problems miscategorizing or miscategorizing birds. And when it comes to, I believe it's eBirds, that where people would try to identify the type of birds, and they kind of get it right, but not quite. There's little problems and little issues where people try to identify certain really key points or key aspects of a certain, let's say, a bird, kind of difficult to find. Try to to really pinpoint accurately a certain type of bird. Also, missing data. Sometimes the data is incomplete or is non-existent, or we know that somebody's actually collected data, but then they forget to actually hit the send button, or sometimes the data just is incomplete. They sent they hit the send button, but they didn't complete or check all the boxes in making that whole data set that they were intended of collecting complete. And that kind of goes in also toward the last part, where it's biasing and properly collecting data. Some people might have in their mind, oh, that bird is definitely a pigeon, but then everything that they see is a pigeon, and that doesn't quite work. So, helping identify these kind of issues throughout the literature was kind of key to helping to then kind of focus my attention on some of the data that was collected. And so the slide that we see here is just an overview, right? An overview of looking at the dust data, specifically data that was collected in 2020, in April 2020, looking at the global dust collection, and then looking specifically here in the United States. So just looking at dust data on the left pie graph, you're looking at basically 26% actually got them like spot on correct, that they identified this is a dust event, or this is a dust storm event, right? And the rest, like the 11% got it incorrect. Like they thought it was like overcast, like really, clouds, and like it is right now in El Paso. We're about to hit hopefully get some rain finally. But they confuse that kind of overcast with obscurations, which is like what we get from a dust storm, or what you would get from pollution or haze. But then the yellow part is kind of a little bit concerning, because it's the unknown. Basically, they weren't able to really categorize, either from the data wasn't, complete, wasn't complete, or it was just inconclusive to look at whether they were able to, identify correctly these dust storms. And so that was the global projection on the A part. The B pie over here, you look here in the United States, we got about 50% correct, but then the other 50 not so much. So we're looking at some incorrect, 27% incorrect identification of dust events, and then 23% were like not too sure. They were inconclusive in the sense of saying that what they were identifying was correct. So I kind of wanted to take a look at how we can overcome these kind of pitfalls. Well, great example, 2017, the eclipse data, looking at temperature data during that eclipse event, was basically solved, if you will, or basically addressed pretty well by looking at the many data points, as you can see right here in this slide, the many data points of people that were collected. A lot of people participated, and so during that eclipse event, as was published by Brandt, Dodson et al. That basically that the more participants that were involved, the less noisy the data became and became much more accurate. And so in numbers in the data that was collected, the number of data points were basically what kind of washed out any kind of noise, and the data became useful, extremely useful, in fact. And so I don't know if you guys can see this over in the side. I'll just move this part here. So some of the methods of basically overcoming these little hiccups, if you will, when it comes to data quality, you just get a lot of data, and that's what Dodson et al. As well as I looked at another I guess you could say planetary analysis, also using citizen science to look and identify um, certain carbon dioxide little pockets that explode on the Martian surface. They basically did something similar. We just collect a whole slew of data to basically filter out the noise. Also collecting, design, and training, and then that's kind of interesting too, because the way how you can actually want to collect data is also important to address that when you're trying to incorporate citizen science, to go out there and actively do this, as well as the training. And that's the one I kind of that drew my attention for my dissertation project here. Training. Why don't we actually get, because we're also trying to get people to not only collect data, but we're also trying to help them understand the environment just a little bit better than where they were was just the day before, right? You want these people to really get engaged, and you really want them to understand why the clouds are doing what they're doing, and what kind of clouds are those, and are they a signal for other things to come. So one of the things I kind of want to highlight when it comes to that, how do we do this successfully? Let's do a better training approach, because then that data becomes more reliable, becomes much more of an educational tool now, because now people are going to be more in tune and want to go back out into the field and really engage, and then encourage more people to collect more data as time goes on. So one of the things that I kind of wanted to address is this part right here. What are some of the training techniques that could actually really help with people, going out there and really, taking really effective data? I mean, really accurate data. And so one of the things that I came across is this thing called what's called model-based reasoning, or MBR. And basically, in a nutshell, basically to use this is basically you're building what's called a mental model of what's going on outside, for all intents and purposes when it comes to clouds. So when we take a look at that, right, when we take a look at model-based reasoning, we have all the participants from all different types of educational backgrounds, right, to utilize all their experiences and bring that to the forefront when they start to then analyze clouds, for example, for this specific example. So what we want them to do is we want them to come out there and then being able to picture, visualize, and then put that on paper in some way, shape, or form, what they're seeing, and being able then to incorporate their experience plus the training that they're getting from online that NASA Globe actually provides for people who are taking this data, to then incorporate that and see how they can actually then digest that, internalize that, and then learn a little bit, and then make those um, accurate should I say those accurate cloud identifications. So it kind of goes like this, right? And so basically think of a flow chart type style. It's not a flow chart per se, but it's in the store flow chart type style, if you will. And model-based reasoning is basically you are doing something like this. So if I were talking about, well, what's a great way to describe, let's say, dust emissions or dust storms, right? Well, what are major causes of dust storms? Well, then you kind of take a look. Well, winds that are increasing, that increase over time. Also, what promotes these dust storms is the fact that you have a lot of, well, desert, for example, right? As an example, the more desert you have, the more dust you have for that wind to really kick up, right? And so here in the Southwest, we have issues that we have to deal with, what's called desertification, where we have deserts that continue to grow, where once there was some sort of vegetation, but then it starts to, unfortunately, due to drought and other causes, anthropologically speaking, you get bigger deserts, so you get more dust. And so you make these little connections, and that's what the model-based reasoning does. It builds these connections such that you can then connect them with these arrows, and it goes right down to where it says dust emission. So increasing winds increases dust emissions. I mean, that's a kind of very basic thing. Desertification increases dust emissions. And so what people are doing with this type of model-based reasoning is they're building these are what we call basically mental models, and then making more connections, connecting the dots. So then they have an idea of how things really work. And so that's what I kind of wanted to bring into this research, and wanted to bring in very to see if this actually really worked and whatnot. So what I wanted to do first, before we even apply this new training technique and see if it helps, with the data collection, data quality of certain of a cohort of globe participants, I wanted to identify some of the common issues or common errors that you might find in some of the data. And so basically what I did was I took a look at, first of all, 500 data points. So basically 500 data sets, 500 people that actually collected data through the Globe Observer app. And this is specifically looking at cloud. So all the data that comes in through that cloud protocol, I analyzed. So basically, I selected 500 participants, basically, and using a bunch of this, wonderful, a little bit of my little computer prowess here, using a little bit of Bash shell scripting and also MATLAB and you name it, I was able to then develop a way to analyze and take a look at people's responses. So one of the things is, if you can see that picture over here to the right, that's almost a clear sky picture, maybe some high level clouds in this one. But what I ended up doing was to see what were, first of all, the participants' judgment on their call of what they saw in that image and what they saw in the sky. And I look at it and I figure, okay, well, then I go in there and I literally, like a teacher, I guess, because they go in there and it's like, did you get that right? So then I go in there and I take a look and see if they actually did, get the actual cloud right. So I did that for all those 500 data sets. And one of the things I kind of wanted to do was develop some sort of a rubric to kind of guide me in understanding the ways of how they responded. So one of the things was to look at correctness type, whether it was a complete correct classification or if it was an incorrect classification. Under and over classification, or under and over counted, that means is that there might be a cloud type that might be in the sky, and everybody might say, okay, that's a cirrus cloud, and then they think that every cloud is a cirrus cloud, including the low level cumulus puffy ones. And they're like, okay, wait a minute, no, you identified, yes, that is a cloud, but not that type of cloud. There are some that are very questionable. Some might actually will have all the data posted, but then they say that there's, like, for example, there are maybe 20% coverage of clouds in the sky, but then they don't label anything, which is kind of weird. And they say, wait a minute, there's some sort of questionable issues with that data. So then there's also things that are the contextual types of when you're looking at these misclassifications, is you're looking at, did they misclassify the cloud type? Did they just completely just forget that there was any data, like you just mentioned? Was there possible bias? Like if they see a cumulus cloud, then every cloud is a cumulus cloud. Maybe they're kind of leaning for that when it's really not. And then I have these general comments. Now, these comments are not what the participants did. All right. These are comments. These are basic comments that I made special note of, that I saw in particular with that particular data set. For example, I might be able to say, boy, there is a lot of bias here, or there's a lot of, people calling that all these clouds are high clouds. So these comments, I tried to standardize them as best I could, and then looked at those comments. And then at the end of this whole analysis, I could have figured, well, which ones were the most common comments that I found to be when looking at all the data. So out of those 500, about 150, about 30% actually got it correct. And the rest got it not quite. They misclassified some of these clouds. And so looking at that was something very interesting, right? So some of that was kind of an issue where out of that we got to see about a 30% overall success rate. Taking a look at that, if you break it all down, if you notice that if you go from A to D, so from A to B, we start to see the red line kind of go down a little bit. And over here in the D part, that D figure, that graph is almost even. Like it looks less red. So what does that mean? Well, that means that if you take a look at the chart A, I actually broke these down into the 4 different types of cloud types that you would actually be able to classify, whether it be contrails, high level clouds, mid level clouds, or low level clouds. And it turns out that the higher it appears that the higher level, the higher the clouds in elevation, the harder it is to identify or classify, as opposed to those that are really close to the ground, those cumulus clouds. Those are a lot easier to classify. There's less error with that. And the mid-level clouds are not, they're pretty much the same thing. And I think that was that was an interesting thing, that the low-level clouds, and actually it pans out with some of the articles and publications that actually have already come out, which was the fact that yes, that there are some the closer you are to the ground, the more accurate your cloud classification is. So that kind of seemed to work in that sense. We have over here in some of this other data. Oh, whoa. Basically, I'll just kind of skip over here just because there is a lot to cover, and I'll give you just the main gist of this. So if we take a look at this overall from the data, taking a look at how many were correct, well, it's about 150. If we kind of break down the overall, how are they getting them incorrect, or how are they misclassifying? How are they misclassifying some of these clouds? Well, I take a look at this and I say, well, some were just, they just appear to be getting it just misclassifying, period. That's where you get the incorrect bar right there. Now the underclassified and overclassified basically are like if they see a cloud, it is a cloud, it's a high level cloud, and then they see everything as a high level cloud when really it might be a contrail, or that's the overclassified. Or the underclassified is like saying, oh, there seems to be a lot in, when I look at them, there's a lot, for example, let's say a lot of high level cloud, a lot of cirrus clouds up in the sky, but then I notice that they don't put it down, but they put a lot of mid-level and they put a lot of cumulus, like low-level clouds. And I was like, well, no, you kind of missed those, and they're kind of just completely not identifying those type of clouds. Although they do see them, they're just not quite putting it down right. And when it comes to the data collection, questionable. It's like, yeah, they see there's clouds. I know you just on your data said that there is some sort of cloud cover, but you say that there's no high level clouds, and there are clearly high level clouds, but then the data is kind of all not interjumbled, if you will, and it's kind of like questionable, like how accurate that collection was. So what are some of the things when I took notes of what were the more common, I guess you could say, like a word, if you want to like a word map in a way, but the 5 words that were the most common when I was writing down these my own analyzing my own notes, is that there were issues that there was, when I keywords here were like mix. What I mean by mix when I was looking at everybody's data? Well, it means that some of the data, some of the clouds were mixed, literally. So you see high level clouds, and all of a sudden you see cumulus clouds. And I noticed that that's when you see high level and low level, or you see some high level and some mid level clouds, which are, as you start to increase, the mid levels are a little bit further away from the ground, and the high levels are way further, a little bit further than that. There is a little bit of like difficulty in identifying them, right? So I noticed that whenever you see that kind of mixed family of clouds, people tend to get a little bit, I guess, a little bit apprehensive of like really nailing it, classification. Difficult when it seems like, I've noticed when it says it's difficult, it means that somebody's taking a picture, and I look at a picture, and it's suddenly a tree, or there's a building right there, and I just see barely a little bit of the of the sky, and I'm thinking, okay, yeah, that's a little bit of a difficult to really validate what verify what they're seeing, right? Missing data. self-explanatory. Some of the days is plain flat out missing. Maybe when they take those pictures, they only take a picture of the north sky and then their feet, and then that's it, as an example. And so that's one of the things is like, okay, we can actually fix. And then we have conditionals where people were making one cloud type for another. Sometimes if it's a cloud type, let's say of a cumulus cloud, maybe they think it's when they classify it as a cumulus cloud, and they're like, oh darn it, no, you're really close, it's really an altocumulus. But I can see why they would make that call. And some of the I guess you could say judgment calls on the participants part, you could just say, okay, you know what, yeah, I get it, it's not yeah, I could see why they're a little bit confused. And then we have data acquisition error, where the photos were just blurry, and that kind of stuff is like, okay, all the other stuff, when they're classifying, I was like, what do you see in the sky? I see cumulus clouds, stratocumulus, and then all of a sudden, when they get all through and done with that part, then they go out to the field and they take pictures. They're like, blurry picture, or the finger is like right there over the camera, and I'm like, no, I see finger. I do not see clouds. So we're like, let's see if we can actually figure this out. So some of the things is that let me just skip to the main top three. There are top three misclassification issues. I should not so much errors, but they're the contrail confusion. Basically, if you take a look at that top right picture, people were kind of confusing the contrails for cirrus clouds and vice versa. And that's kind of easy to see, especially here in the El Paso area. Just recently, there have been a ton of air traffic recently, and there's been a lot of high level clouds, a lot of cirrus clouds that are up in the sky lately as well. And you can really understand why some people, and even for me, there have been a couple of times when I would actually go outside myself, and I could understand from the globe participants' viewpoint, they could really mistake a contrail for a cirrus cloud. That's understandable. And so that was one thing I kind of want to say, maybe we can address that. The cumulus conundrum. Okay, that's a really interesting thing, where we have issues with how do we differentiate between cloud type. All right, so we have cumulus clouds, but we have altocumulus and cirrocumulus. So there's three types actually. And so how can we really determine those differences? Well, one is really close to the ground, and the other extreme one's way, way, way up in the sky, way high in elevation, in altitude. So, I mean, those are some things that kind of might be of interest, and maybe we can actually tackle this with the new training approach. Now, coexisting clouds, if you can kind of see that in the bottom right picture, this is just an example. You see cumulus, but off in the background, you do see some cirrus clouds. And so people would, when you would see that, that perspective, they're looking at those issues, and you're like, geez, it's like maybe that's a cumulus cloud, and maybe the ones in the back are cumulus clouds. So looking at that kind of response, those kind of responses, I figured there might be a way that we can address those through specialized training. And so that's where the model-based reasoning comes in. So now we've already looked at all those issues that are concerning with data quality. Now, how can we address them and maybe make it a little bit better? So in the aspect of time, let's just go ahead and take a look at this. So I went ahead and I took a look at dividing two groups, traditional and model-based reasoning groups. So these are students that were and also globe participants over the summer of 2022, and looking at some of these people who were there that were really interested, but only got 11 people that really wanted to participate in doing what's called the traditional way, which is meaning you get your app, you download it, you install it, you go through the quick training and maybe some online training modules that are available, and then they go outside and then they go and take observations. The model-based reasoning one is, okay, well, the model-based reasoning is you go through all of that, what I just mentioned, plus a little bit of a twist of basically bringing in the model-based reasoning techniques that I mentioned, drawing those little circles, like the little flowchart approach, and making mental models, and then going out and then taking a look at some of the clouds. So basically that is what this slide talks about right there, okay? So going off to the next is when you do the model-based reasoning portion, you basically cue them, the students, once they've gone through the training, and you want them then to do an activity. before they go out and they do the observations, you want them to actually do this model-based reasoning activity, and the activity prompts them with these different types of questions, and each of these questions are addressing the contrail confusion, the cumulus conundrum, and the coexisting clouds issue. And so basically what they do is I fashion 4 different types of questions so that they can actually go back and say, okay, how do we what are the differences between a contrail and a high level cloud or cirrus type clouds? What are those, as an example? Like I pose them a question, and then they draw little bubbles as a cirrus cloud is different from a contrail because XYZ, and then they build like this visual map, mental map on paper, and then they see how they can do that and see if they can actually do a better data collection. This is the online training that they went through. This is an example of, for those people who are doing the model-based reasoning portion of this study, this is how they would actually draw this, and they actually draw these nice little these mental models right here using what's called concept mapping. And concept mapping is really, really effective in many avenues of education. So I think mental models using the concept map approach, super great way of actually visualizing certain topics and see how everything is connected. And using a rubric to judge how well they did on their concept maps, I use that to take a look at then their observations when compared to just your good old traditional training group, right? And so I get out of the traditional group, which were only 11 people, they actually collected 80 data points, if you will, or data sets. The model-based reasoning, out of only the 7, they collected 56. So that's actually not bad. They were actually relatively pretty active in doing this and participating. And of course, me got to go into the data and really see how well they did. And that's basically downloading the data from the data globe database, taking a look at that Excel spreadsheet, and then doing a little bit of prettying up of the data so I can actually take a look at it, as you see in this picture, and identify whether they got their classifications right or not. And I wanted to see if there was any kind of correlation between the data that they collected and the observation scores versus how well they, like, this is for the model-based reasoning, if there was any correlation with the observation scores and how well they did on their concept maps. Like I would, using that rubric, I would grade them. And there doesn't seem to be much as far as a correlation regarding that. Let's see if there's any improvement with model-based reasoning versus traditional. There is a slight improvement using model-based reasoning. So out of the classification accuracy, about 78.3% from the model-based reasoning group got when they went through that specialized reasoning versus the traditional, which got 77.9, or basically 78, almost the same. So I mean, it's neck and neck. So we wanted to do a breakdown of that. We did a data analysis of this, and so how well did they do in these those people that scored in this is data right here for the model-based reasoning group, the ones that actually went through that specialized training. The orange is just your cumulative, everybody who scored on their model-based reasoning, how well did they do? Overall, in the orange, they had 78.3. That's what we just saw on the previous slide. The 78.8 one, that's when these are the people that didn't score too well, but they were able to, react or interact with the data. I mean, with the model-based reasoning, concept mapping, and everything, they seem to do better, which is interesting. Those people who scored, average, they didn't do so well. They did as well as those that were in the traditional training. For those who really, really scored well, or really, really scored high on their concept maps, they got an overall, when it came to actually going outside and looking at the clouds and classifying them, they got up to 78.9. So looking at that data, there seems to be some improvement. Is it notable? Some, not really. I mean, the fact that there was training and using these concept maps helped. There was a lot of questions later on, I think, when people would actually submit their work and whatnot. it was interesting to see that, but there wasn't really any significance between the data, between the training and the model-based reasoning training. So that was a bit of a yeah, a little bit of a take back. But I think one of the things, if we break it down, and like I said, due for the instance of time, if you take a look at this data right here again, if you break it down by, let's see how well they did with um, high level clouds, mid level clouds, and whatnot. Again, it's up and down. It just seems that overall that the end result, let me just get this, the end result is to give you an idea, is that as long as there seemed to be some sort of interaction of them with the training that they get, it seems like it overall in the end helps. Here is an example right here of like the question that I would pose to them, and this is an example of a really good what is it, a concept map for the model-based training group. Doesn't seem that detailed. So this is what I consider the lower end of the grade that they would have gotten for their concept maps. And they're like, why? I mean, they could have gone a little bit more, but they seem to be a little bit more responsive in the sense that as long as you get some sort of feedback from them, it seems to be going good. I'm going to skip to this other part as far as the overall conclusions from this. And I think overall, I think that what we get to see from the model-based reasoning group, that it could mean that even though there wasn't that much difference between the traditional and the specialized model-based reasoning techniques for the training to help them with their cloud classification, didn't seem to be that much difference between them, statistically significant, at least. There were some interesting things that I was able to take away from, and through further discussion after the research, I think might be useful for us when we go out and we use this when we teach. And I think some of the people who have been, I think some of us in today's group here for the Watercooler remember 2019 over there in Denver when we went to do that workshop. And so the workshop was basically where I got the idea for my dissertation, where there was a storyboard approach to looking at storms and different types of weather systems that came across the Denver area or in the Colorado area. And this was to help us. This workshop, believe it or not, was here to help us address those things. How do we get students to learn a little bit more and understand how everything works when it comes to climate? So there is the little QR code for those of you who are interested of getting a little bit more information on that. The storyboard approach is a great way of doing this. I mean, you walk your students, but this is from a classroom perspective, right? That you're looking at getting your students and identifying, let's say you give them an incident or an event. Let's say in this case, there was a big flooding event that was I don't remember all the details, but I remember there was a flooding event that was like a once in 100 years type of event that occurred in Colorado. And they wanted to identify what were the signals in the atmosphere that basically brought about this type of a storm and that brought about this deluge of water that basically flooded this particular area in Colorado. So then they do what causes storms to form. And so these were the type of questions that they prompted. And we went through this approach, and lo and behold, during this 2019 talk, there was this continuation or this approach to a model-based reasoning type of approach of learning about weather. And that really, I think, if you were to take the weather curriculum workshop approach that was done here in 2019 over there at NCAR, you could actually use the model-based reasoning to really then pull out even more details to where you can actually train better and have students learn a little bit more about the weather. But at the same time, it might be a good idea to also bring in that into the training aspect, which is something I plan on doing on further researching on this, is not to expand a little bit more on what I did for the dissertation. Was, yes, we understand these misclassifications. We know what they're doing. We understand that the training is helping, but maybe now using this approach with what we basically from this workshop, maybe we can incorporate the approach of looking at the event as a dynamic event, looking at all the different pieces that come together, and then using the model-based reasoning then to look at it as a full-blown story, as opposed to more of a static, here's a cloud, let's identify it and its properties. Maybe identifying the whole picture of like, oh, we see clouds coming, and we see this other bunch of clouds coming. Maybe something's happening. What is that happening part? Can we include into the model-based reasoning? So that's something that looking to the future, how that works. And then we have this other awesome piece that where we can also incorporate the model-based reasoning and story maps and using the concept maps to then go into the classroom. And Adriana, this is what we worked on, and then it's just recently got published. I think some people already sent emails to everybody about this one, and this is a great way to actually then continue that visualization, to continue that educational approach, to where you can actually just go and learn more about the NASA Globe program this way. And then what we did is we basically built a using the Globe Observer data and also my NASA data as well, to then go into the classroom, have students go out, look at the clouds, identify them, look at the data, identify the data, learn a little bit about how to interpret that data, and then utilize that data to then answer additional questions about the weather and whatnot. And I think, I think that's, yeah. So there we go. So I think that in a nutshell, and I'm going to bring it to a close because I think we are at time. So we're going to take a look at this. When you look at all of these tools that are available, the model-based reasoning, the workshop that was presented in 2019 at UCAR, and then incorporating the model-based reasoning into that, we see that here. And for anybody, there's a QR code if you want to check it out. So just like plug. If you want to take a look at it, definitely see what the learning module that we actually developed, and we're using them right now in our class. I'm using them in my classes. I'm going to be using them in my spring semester classes for my freshman and sophomore students at EPCC at the Paso Community College, and I believe Adriana is going to be using it as well as for the early college group students that are going to be utilizing globe data all the time. And so it's great. But one of the things is incorporating all of these techniques. And I think that even any kind of modeling or any kind of mental models, bringing in the specialized training can really engage people, especially in a classroom setting. The module that we developed here and utilizing the concept maps as well, and really getting people to go outside and just look up. And I think it's one of the greatest things that people can do, to bring the outside into their mind and process it, and then really start to connect with what's outside. And I think learning is part of what the Globe mission is for. And I think this is just one of those things that we can actually continue on and really grow in. And with that, I will finish. So thank you very much.
Thank you, John. So with that, there were hands raised. So it was Larissa and Mike. Both had your hands raised for questions for John. I don't know who, Larissa, you want to go first? So John,
Yeah.
thank you though very much for your presentation. It was awesome.
Oh, thanks.
All right, Larissa.
Yeah, very quickly, John, thank you. Excellent and very needed work. So kudos to you and congratulations on your doctoral, really unique, really title and information provided. Thank you. Great presentation. So I guess the natural next sort of step would be to really see what can we do, how we can use AI algorithms that will be automatically check data for errors or anomalies. So any data validation and corrections. So do you envision any work in that direction? Are you working with Globe Observer on making those steps? Any AI sort of updates and thoughts, if you have any? Thank you.
Right. I think in the process of actually doing this dissertation project there was talk about that machine learning, actually looking at that and identifying clouds like
Yeah.
before. And so that there is that work. And I think some of the stuff that came out of here and tying it in also with concept mapping or the work that's established here can actually go really well with that. And I think that it's already been it's in development as we speak, and in doing so. So AI is going to be a major component, I think, in the future when it comes to specifically to this with identifying clouds. Yes, I do see that.
Yeah, thank you, John. And very quickly, just a quick comment that thank you for bringing up the MBR. And I think for educators, it would be very, very useful to really, in a very simple terminology, to explain what's the difference between MBR and, in general, all predictive modeling, because sometimes there is a confusion between model-based reasoning and the predictive modeling, because they are related concepts, but they have different sort of features. So thank you. Yeah,
Yes.
thank you, John. Congratulations.
Oh, thank you.
So,
All right.
John, thanks for a great presentation. I just on your one of your very first slides, you had you said missing data, but you had dismissing data on your slide. And I wondered, no, but because I think that's a common thing that happens. I think we have, I'll put it on students, whether they're big or small, right? I think sometimes they dismiss data, right? They don't, I don't know it. We can explain it away and say they missed the button, they didn't click the button, or they didn't see it. I think sometimes they don't do it. They flat out just dismiss the data. So I wondered if you, I think both are kind of interesting. So I wondered, what did you mean, missing data or dismissing data?
Actually, it was actually both. I did see that. And it's really hard to decipher because you're looking at data and you don't have that one-on-one feedback with the participant directly. But what you can see, especially if that individual, because out of those participants, they'll take another data collection on another day, and if I recognize that, according to that site ID or the participant ID, all anonymous, but if I notice that, oh, it's the same person, then I look at that and I kind of see maybe a pattern. Then yeah, I notice that, oh, it appears that they might be actually dismissing the data. You're like, nah, this not gonna even count to my mind, as opposed to just missing it. Yeah. And so those are the really tricks. Looking at the data is just at face value, it's really difficult. It's kind of to figure that out. But yeah, I get it is my impression, my understanding that there is some of that dismissing of that data, believe it or not. And so I think that is something later on to really look at when you look at, like, if you incorporate, instead of just a static view of actually, with the model-based reasoning I was telling you right now, if we actually did something that's more dynamic, like tell a story. When you're telling a story, that dismissing of the data becomes less apparent, because you're forced to then go back and say, okay, well, you're trying to connect the dots to understand this story completely. So you're then doubling back, so you don't dismiss the data. You actually start to incorporate it more. So yeah.
Yeah. No, it's a conundrum, because it's similar to the one where blanks and zeros are not the same thing, right? A zero is actually a data point. Leaving it blank doesn't, even though you think it may be, it was a zero and you don't record the zero, right? That's
exactly.